Hello, everyone. Welcome to our junior design project presentation. I'm Munguia Torres,
And my name is Jalen Solis.
and today we're going to be going over the project that we made called Cyclone. So throughout this presentation, we're going to go through four main things. The first one is going to be the project overview. Throughout this part, we're going to be basically showing what we wanted the project to look like at the end and how we were going to get to that final project. The second segment is going to be the black box. Here we're going to show all of the modules within our project and all of the sub-modules that we're going to be using to complete the task. Next, we're going to go over some of the problems we faced along the way and how we managed to fix them and how that translated to some useful lessons we learned about making software like this. And lastly, we're going to have a quick demonstration of our project to show the final product. So first, we have the project overview. So if you guys don't know, this is what a Cyclone arcade machine is. It's basically an arcade machine that has a light rotating in a circle continuously. And the objective is that the user has to press the button and make the light stop at the correct point. And if they stop at the correct point, they get a bunch of tickets. And if not, well, they lose. We wanted to recreate this on the DE2-115 board as best as we could. And to do this, first, we have to add a start and stop function, obviously. So the player would get to choose when to start playing the game and what the game started. And then obviously they have to press the stop button to stop the light when it's moving and finish the level to move on to the next level. Then we would implement a moving lights function. So the DE2-115 board doesn't have circular lights like a traditional Cyclone machine, but we were able to use the 18 red LEDs and have a light moving from one side of the board to the other and then back to simulate the movement of the original Cyclone machine. And then next, we would implement a win condition to determine that the player has won. And this only happens if the player lands the moving red LED light under the only green LED light labeled LED green 8 on the board. That is the only one that is above the red LED lights. It'll make more sense during the demonstration, showing the placement of the green LED light. But if they land it right under it, they win. Conversely, if they land anywhere else, that would be a loss. So that's the lose condition. If they stop at any other point besides the green LED light, the player loses. And then we also wanted to implement layers of difficulty. So to do this, we wanted to increase the speed as the player won multiple games. So we wanted to add a system that when the player wins 3 games, the speed doubles. Or like the speed of the lights moving would double. This excludes the very first level, which would act as a tutorial level. But after that, every 3 rounds that the player wins, the speed will double. Next, we wanted to keep and display the scores to the player so the player could see how much they're doing and try to get like a high score. So on the 7 segment displays on the board, we would be displaying the current player's score. And then we also wanted a few results depending on how the player does. So if the player loses, if they don't land the light at the correct position, then their score resets to 0. The speed will obviously reset back to 0, so like the difficulty starts over. And the 18 red LED lights would start flashing. They'll flash 3 times, on and off and on and off, to indicate that the player lost the level. And then conversely, if they win a level, the same thing happens, but with the 8 green LED lights to showcase that the player won the level, and then they'll get 100 points for winning that level. And then lastly, there is a way to actually beat our Cyclone game. If you get to 12,000 points, if you accumulate that amount, you technically beat the whole game, and then the game restarts from 0, and you start over.
Okay, so now we'll be going over the diagram of the module and submodules. So the main components of this project consisted of getting the user's input to control the LED lights. The LEDs would then turn on and off and would give off the appearance of motion. The module would then check if the player had won and would display the results accordingly. Diving in a bit deeper, we can see all the input and outputs of the module, as well as a more accurate description of the module's components. The user begins by pressing start to activate the game. Once the game begins, a red LED will start from right and move all the way to the left side of the board, and then back to the right, and so on and so on. A green LED will light up, which is where the user must stop onto to progress the game. If the user stops on the green LED, the board will output all the green LEDs and the score along with it. If the user fails, the board will output all the red LEDs as well as the score to go along with it. Finally, if the user beats the entire game, the green and red LEDs along with the final score were output from the board, indicating to the player that they have won. Additionally, the reset input is there in case the user wants to ever end the game early or an error occurs. Okay, so alright, so now we'll move on to all the lessons learned and the problems that we faced while working on our project. So the first issue that we came up was timing. So the human eye is limited to see a light blinking from 0 to 30 hertz, and the DE2 115 board had an internal clock of 50 megahertz, so it was moving way too fast. And when we tested it in Model Sim, it worked flawlessly, but again, it was outputting in picoseconds, which is too fast for anybody to see. So we needed the speed to change as the game progressed. So a solution that we found out was adding a counter module to slow the clock. So what the counter module does is that it counts to a certain binary number depending on our input and returns only 1 bit. So this allowed us to maintain the speed of the clock based on the input that we sent. And the lesson that we learned from this was how to manage the internal clocks of the hardware to make sure our system works as intended. So knowing how to slow and speed up the clock is very important for this project. The second issue that we came up on was how to output the score. So we had to turn a 4-digit number into 4 separate 1-digit numbers. We had to have a way to keep count of our current score, reset it, and then add to the score while the game progressed. So a solution that we came up with was we decided to increment by 100 to keep the last 2 digits constant, which would make it a whole lot easier when trying to add the score up. And we used the modulus and division operations to separate the 2-digit numbers into 2 1-digit numbers. We kept an internal counter that incremented whenever the green LED turned on, which meant that the user did win the game, and then the counter would reset if all red LED lights were on simultaneously, which meant that the user had failed the game. And then the lesson we learned from this was that by displaying large numbers is as difficult in a 7-segment display. However, it is useful and can be used to separate the digits in order to make it more manageable. And then the final issue that we had was that we had accidentally added latches to our main module that compiled correctly in Model Sim, but when we went to go test it out on our hardware, it failed. So a solution for this problem was we just added more cases. So we followed the compiler's advice and removed all of the inferred latches that were present in our combinational logic. So we had to find an alternative way to get the same result. So we decided to add a few extra states to our FSM machine in order to resolve the issue, which was a little bit time consuming, but it was pretty easy to do, and it gave us the correct solution to our project. And then the lesson that we learned from this was that System Verilog is not a coding language similar to C++ or C++, so it should not be treated as such. Adding latches and asking the system to infer them can lead to many errors, so they should be avoided at all costs. All right, and then now we'll see a demo of our presentation.
The first thing I want you guys to notice is right here, where I click the left mouse button, which starts the game, starting the red LED light's motion, and turning on the green target LED light. seen next to the 7-segment display. You can see here the light is moving, and it only stops when I click the rightmost button under the green LED light, showing that I won. And as soon as that happened, my score also increased. And if you look on the right side, right above my finger, you see the 8 green LED lights flash on, showcasing that I won. Here you see the speed increasing as I won the 4th game. Again, you see my score increasing as I win the game, landing that LED light at the correct place. And here once again, the speed increases as you win more and more levels. And lastly, here you see the losing section where all the red LED lights flash on, kind of like the green lights did earlier, and the score reset, and it's ready for you to play again. Now I'm just going to play the entire clip in its entirety without pausing so you guys can see how it moves in real time. And also I wanted to showcase that after you lose, you can jump right back in and play a new game. And lastly, I just wanted to show how all the LEDs turn on when you win the game. So I'd like to thank you guys for listening to our presentation.
Yeah, thank you guys for listening, and hopefully you enjoyed this.